Hi, my name is Leah, and I'm going to be presenting the work from the 2024 AAS AIAA Astrodynamics Specialist Conference titled Spacecraft Dynamics Containing Prescribed Motion Platforms with Dynamic Subcomponents. So this work is motivated by the question, how do we expand the back substitution method to include forking spacecraft configurations? So in the next few slides, I'm going to be going over what the back substitution method is and how this work is seeking to expand it. So the back substitution method leverages a hub-centric spacecraft configuration with parallel component connections to the rigid hub. So these concepts are illustrated in this figure here, where we see a centralized rigid hub in gray and rigid components, also called effectors, in blue here. And so under the assumptions of this method, we can only attach components sequentially or in a chained manner relative to our hub rather than in a forked configuration. And this is because when we connect these components sequentially, there are no effector on effector cross-coupling terms that show up in the system mass matrix. So there's only specific effector on effector components in our mass matrix. So there is not a cross-coupling. And this allows us to invert our system mass matrix using only 3x3 matrix inversions rather than invert the entire system mass matrix. And I'll be going over that as well in this next point here. So the back substitution method was developed to address two significant challenges of implementing the dynamics of complex multi-body systems in simulation software. The first challenge, like I mentioned previously, is inversion of a large system mass matrix. So on these equations on the right, we can see that we can write our system equations of motion with a mass matrix on the left-hand side multiplied by our system acceleration vector. And then we can bring all the other terms that are not coupled with this acceleration vector onto the right-hand side. And so in order to solve for this acceleration vector, we would want to invert this mass matrix. However, the computation of this inverse can scale with the cube of the number of states. So especially for very complex systems where we have numerous different components attached to our hub, the inversion of this matrix becomes more computationally intensive. And then the second challenge that this method seeks to address is the modularization of the system dynamics. So essentially, when we view this, these equations on the right, the system ultimately needs to populate this entire mass matrix. So it needs to know the hub relative and component relative locations of each component in our system. And so to implement the equations of motion of large multi-body systems in software requires that the system needs to know so much information of each of these components. So this method was developed to essentially modularize the dynamics of each component and kind of remove that burden from the spacecraft hub and ultimately break up the different components of the dynamics of each effector, and then essentially solve the system equations of motion in a modular way. So I'll be going over that as well in this next slide. So to illustrate the points from the previous slide, we can first write our component accelerations in terms of the hub accelerations here. So our hub translational and rotational accelerations. And then the component accelerations are these alpha terms. So keeping this very general. And so the terms that are coupled with our hub accelerations and our equations of motion are this A and B term here. And so substituting these equations back into our system equations of motion, allows us to explicitly decouple our system equations from these effector accelerations, and we can write our system equations of motion in the simplified form, where we only need to perform 3x3 inversions, as seen here of these A, B, C, D terms. So now that we have our hub accelerations, we can then back substitute these accelerations back into our component acceleration equations. So these are the basics behind the back substitution method. And this is kind of illustrating both of these challenges and how the back substitution method seeks to resolve them. So now I wanted to just go over the allowable and unallowable spacecraft configurations under the assumptions of this method, and how this work seeks to expand the allowable simulation space. So first, we just have this hub-centric parallel configuration. We have two different components attached to our hub. And so first, there's been a lot of work done to develop the equations for force torque actuated components that are connected to our hub. So some previous work has been done to develop the dynamics of N hinged solar panels connected to our hub. Work has also focused on N sequentially rotating and translating bodies connected to our hub. And then also we currently can attach prescribed motion components to our hub. And the difference between these components and the force and torque actuated components is that we assumed that there are no equations of motion to integrate for these prescribed motion components. So you can think of components such as solar panels or gimbals that are actuated by motors. And we can essentially write profiler modules to feed the current states of these components into our system equations of motion. And so this assumption essentially requires that the dynamics of other components that are attached to our spacecraft don't influence the motion of these prescribed components. And so here we can see that we can currently simulate parallel connections of these different components onto our hub. And then another type of motion that we can currently simulate is prescribed motion forking. We have a fork on the left and on the right. And these types of configurations are allowable under the assumptions of the prescribed motion, where in order to derive the dynamics of these bodies, we assumed that the states are profiled relative to our hub. And so this essentially enables us to connect these components in any configuration that we'd like. So for the unallowable configurations, we have a closed chain, and we cannot simulate this type of configuration because we have cross-coupling terms between effectors that show up in our mass matrix that removes the ability to invert our mass matrix, as I showed on the previous slide. And then we also cannot currently simulate general fork configurations for the same reason that we see cross-coupling terms show up in our mass matrix between these effectors. And so this work seeks to allow prescribed motion relative forking, where we see a prescribed motion component that's directly connected to our hub. And then we'd like to allow parallel connections again relative to this prescribed motion component. So we're seeking to enable one level of branching relative to our hub by passing on some of the responsibilities that the hub had to these prescribed motion components. And so just to discuss an application to show the usefulness of this configuration would be a spacecraft with a prescribed motion boom that is actuated by motors in green here. So it could telescope outwards or rotate or unfurl. And then we might want to add other force torque actuated components like these smaller solar panels onto these prescribed motion booms. And so I'm going to be referring to each of these components as a multi-body actuator component, where we see a prescribed motion component with n number of force torque actuated components connected in parallel to it. So the problem statement for this work considers 5 coordinate frames. The first is an inertial frame. The hub frame is this B frame. The prescribed motion frame is this P frame. And then the prescribed motion is profiled relative to this mount frame M. And then in this derivation, we only consider a single force torque actuated component, and the frame of that component is designated by S. However, we can expand this derivation to include n number of these force torque actuated components. So next, I just wanted to show quickly the equations of motion for this system. So we use Newtonian and Eulerian principles to derive the translational and rotational equations of motion for the system by considering all of the bodies in the system, and to write these equations in the back substitution form I showed previously. We've isolated our hub accelerations on the left-hand side, and then we've brought all other terms to the right-hand side. And we can see here, these important terms are the accelerations, the hub relative accelerations of the force torque component, and these primes indicate hub relative time derivatives here. So we essentially need to derive the equations of motion for this subcomponent and decouple our subcomponent equations, and then substitute the translational and rotational accelerations back into our system equations of motion. So here we have the translational and rotational equations of motion for our subcomponent, and we can see on the left-hand side, these accelerations are relative to the prescribed component they are attached to. So now we need to decouple these equations to individually solve for our translational and rotational accelerations. So we can do that easily by inverting this matrix on the left, by writing our translational and rotational equations of motion in this compact form. And now that we have isolated the translational accelerations, we can then write them in terms of our spacecraft hub, as seen here. So we've transformed the hub relative acceleration of the subcomponent. We've written the prescribed motion relative translational acceleration as the hub relative acceleration here. And then we've also written the hub relative angular acceleration of the subcomponent relative to our hub fixed mount frame here. So now we substitute those accelerations into our system equations of motion, and we can write our system equations of motion in this back substitution form, where our A, B, C, D terms are shown here. And we can see this is the vectran, so the right-hand side of our system translational equations of motion. And we can see that we've removed the dependence of this equation on our force torque actuated component accelerations here. And then we have our right-hand side of our system rotational equations of motion. And again, we can see that we do not have a dependence on our force torque component acceleration relative to our hub here. So in conclusion, this work leverages the back substitution method to derive the generalized equations of motion for a spacecraft containing a central rigid hub, a single rigid hub-connected prescribed motion body, and a single rigid force torque actuated subcomponent. The modularity of the derived formulation enables us to add n of the force torque components to the prescribed motion body, and then m of the described multi-body actuator components to the central spacecraft hub. And then future work involves software verification of these derived equations of motion that we've presented using angular momentum and energy conservation principles. So thank you for your attention, and if you have any questions, feel free to email me or my advisor, Dr. Schaub.